Welcome to another deep dive. You've brought us some really interesting stuff this time, all about vectors, specifically how to break them down into components.
Yeah, it's a super important concept, really fundamental for both physics and engineering.
Definitely. So before we get into the nitty-gritty of how to actually do it, let's just quickly refresh. A vector has both magnitude and direction.
Right. Exactly. So think about driving a car.
Okay. Yeah.
Your speed is the magnitude,
Mhm.
and the direction you're heading in, well, that's the direction. So to fully describe your movement, you need both,
Makes sense.
and that's your vector.
Perfect. Now, the materials you've shared go way beyond those simple up, down, left, right examples. We're going to explore how to decompose any vector, even ones at odd angles. You'll be able to break it down into components along any two perpendicular axes.
Yeah.
It might sound a little abstract right now, but stick with us because it's seriously useful stuff.
Yeah.
You even sent over this interactive simulation
Oh, yeah.
from Open Educational Resources, open source physics at Singapore. It's called, and get ready for this, Decomposition of Invariant or Moving Along Axis, Vector, along any two perpendicular axis advanced JavaScript HTML5 applet simulation model.
It's a mouthful.
I know, right? What a name.
But don't let that scare you away.
Yeah.
Think of it as like a playground for vectors.
Ooh, I like that. A vector playground.
There are sliders to control the vector size and the angle. You can spin the axis around, and it even shows you how the components change with these cool animations. Plus, there's a random vector generator, so you can really get some practice in.
I love it. So to kick things off, why don't we just play around with the simulation for a bit, see what it can do.
Absolutely. Let's dive in.
All right. So one of the coolest things about this simulation is that it lets you move beyond just that usual horizontal and vertical breakdown, you know?
Yeah.
It really emphasizes that you can choose any two perpendicular directions as your axis to decompose a vector. And that's going to be so helpful when we start talking about forces on inclines or projectile motion or anything moving on a curved path.
Absolutely. It's super important to remember that.
Yeah, for sure. Okay, so we've got this awesome tool, but like why? Why even bother decomposing vectors in the first place? What's the point of breaking this single vector down into parts?
That's a great question. It might seem like extra work, but it actually makes things a lot easier in the long run.
Okay.
Think about it this way. You're trying to push a heavy box across a rough floor.
All right, I'm picturing it.
So the force you're applying is a vector, right?
Right.
But not all of that force is actually going to move the box forward.
I see where you're going with this. Some of that force is just pushing it down into the floor because of the angle.
Exactly. So decomposing the force lets you separate out the part that's actually pushing it forward versus the part that's just pushing it down.
Okay.
And that makes analyzing the motion of the box way simpler.
I see. So instead of one kind of complicated force, we have two simpler ones acting in different directions that we can, like, wrap our heads around a little easier.
Right, exactly. And then once we have those two components, we can use some basic trigonometry to figure out exactly how big each part is.
Ooh, trigonometry.
Yeah.
Now we're talking sine, cosine, all that fun stuff.
Yep. Sine and cosine are basically our tools that help us measure how much of that force is acting in each direction, based on the angle of our original vector.
Okay.
And the simulation, it really helps us visualize all of this. You can see how the sine and cosine functions actually relate to the lengths of those components.
Right. So we're not just like memorizing formulas here. We're seeing how it all works in real time.
Exactly. And the best part is, once you understand how to decompose vectors this way, you can apply this to, well, basically an endless number of real-world problems.
That's particularly...
It's the foundation for understanding everything from how bridges are designed to how video game characters move.
This is getting really interesting. So we've established that decomposing vectors is super useful and that we can use sine and cosine to figure out the components.
Yeah.
But how do we actually do it? Like, where do we even begin?
Well, first, we need to choose our axes. Remember we talked about how we have the freedom to choose?
Right.
So it's important to pick directions that actually make sense for the problem we're trying to solve. Like, for example, if we're analyzing the motion of a ball rolling down a ramp, it would probably make sense to choose one axis parallel to the ramp surface and the other one perpendicular to it.
Okay, so our choice of axes, it kind of sets the stage for how we're going to analyze the motion.
Exactly. It gives us a framework to work with. So once we've got our axes set, we need to measure the angle between our vector and one of those axes. Now, the simulation, it has a handy little protractor for this.
Oh, right.
But in real-world problems, you might need to use a bit of geometry to figure it out.
Gotcha. So we've got our axes. We've got our angle. Now it's time to unleash the power of SOHEHHEOA.
You've
Yeah.
got it. Let's say we want to find the component of our vector that lies along, let's say, the x-axis.
Okay.
SOHCAHGOA tells us that the cosine of an angle is equal to the adjacent side divided by the hypotenuse.
All right, bear with me here. How do those sides and hypotenuse relate to our vector and its components?
So think of the vector itself as the hypotenuse of a right triangle.
Okay.
The component we're looking for, the one along the x-axis, is the adjacent side, and the opposite side would be the component along the y-axis.
Ah, I see. Okay, so to find the x component, we just multiply the magnitude of our vector by the cosine of the angle.
Exactly. And to find the y component, we'd use the sine of the angle. Because SOHCAHTOA tells us that sine is opposite over hypotenuse.
This is starting to click.
Yeah.
But hold on. Isn't decomposing a vector supposed to make things simpler? Now we're adding in trig. How does that actually simplify anything?
Well, think back to our box pushing example.
Okay.
By decomposing that force, we've separated out the part that's contributing to the box's forward motion from the part that's just pushing it down.
Right.
This actually lets us apply Newton's laws of motion separately to each component, which makes the calculations way easier.
So instead of dealing with that one complicated force at an angle, we have those two simpler forces
Exactly.
acting along our chosen axis.
Exactly. And this approach, it works in so many other scenarios too. Like, for example, in projectile motion, we decompose the initial velocity into horizontal and vertical components. And that lets us analyze how far the projectile travels horizontally, how long it stays in the air, all using those equations of motion you might remember from physics class.
Wow, so something like calculating the trajectory of a baseball after it's been hit, that uses this concept.
Totally. Or think about designing a bridge. Engineers need to decompose the forces acting on the bridge to make sure it can withstand the weight of traffic and the forces of wind. By breaking down these forces into components, they can analyze how much stress each part of the bridge will experience.
It's amazing how something that seems so abstract, like breaking down a vector into parts, is actually the foundation for so many real-world applications.
It really is. And the best part is, we're just scratching the surface. Once you grasp the core concepts of vector decomposition, it opens up a whole new world.
I'm feeling a lot more confident about this. We've talked about choosing our axes, using SOHCHA2A to find the components, and even how it simplifies things in real-world situations. Is there anything else we need to cover before we move on?
Well, there is one common pitfall that people often run into. Remember, decomposing a vector doesn't change the vector itself. It's just a different way of representing the same information. It's like translating a book into another language. The story stays the same, it's just expressed differently.
Ah, so the original vector, it's still there, pointing off at its original angle. We've just broken it down into parts
Exactly.
along our chosen axis to make the analysis easier.
Precisely. The magnitude and direction of that original vector, those stay the same. We're just expressing them in terms of components along the axes we've chosen.
That's a really important distinction. So we've mastered the basics of decomposition. What's next? Where do we go from here?
Well, the simulation we've been using highlights one really cool feature. We can actually rotate the axes. That means we're not stuck with just horizontal and vertical. We can choose any two perpendicular directions we want.
Wait, why would we want to rotate the axes? Doesn't that just make things more complicated?
Not necessarily. Sometimes those standard horizontal and vertical axes aren't the most convenient or intuitive.
Okay.
Think back to that ball rolling down the ramp.
Yeah?
Choosing axes aligned with the ramp, it makes analyzing those forces so much easier.
Oh, I see what you're saying. It's about choosing the coordinate system that best fits the problem.
Exactly. And this flexibility opens up a whole new level of problem solving. We can tackle situations where the motion isn't just along straight lines. Think about planets orbiting stars or cars going around curves, anything with curved paths.
I'm realizing this is way more than just a math trick. It's like a different way of looking at the world, understanding how things move and interact.
You're getting it. That's what makes vector decomposition so powerful. It's not just about formulas and calculations. It's about seeing those underlying patterns and principles that kind of govern the universe.
Okay, I'm officially hooked. Let's talk about some of those more complex scenarios where rotating the axis is essential. I want to see this play out in the real world.
Let's do it. There are tons of fascinating examples we can explore.
Yeah.
Okay, so let's really get into how to actually do this, how to decompose a vector. Remember, we're using this simulation as our guide, but these steps apply, no matter what tool you're using.
Got it. So I'm looking at the simulation, and I see this vector just pointing off at like some random angle. Where do we even start with breaking this thing down?
First step, we got to choose our axes. And remember, we've got the freedom to choose, so it's important to pick directions that make sense, for the actual problem we're trying to solve.
Right.
So, let's say we're analyzing the motion of a ball rolling down a ramp.
Okay, yeah. Classic physics problem.
It might make sense to choose one axis parallel to the ramp's surface, and then the other one perpendicular to it.
Okay, so our choice of axes, it's kind of setting the stage for how we're going to analyze the motion.
Exactly. It gives us a framework to work with. So once we've got our axis set up, we need to measure the angle between our vector and one of those axes. Now, luckily, the simulation has a little protractor built in, which is super handy.
Oh, nice.
But in real-world problems, you might have to use, some geometry to figure that out.
Okay, gotcha. So we've got our axis.
Yeah.
We've got our angle. Now we're ready for SOH, CATHTOA.
You got it. Let's say we want to find the component of our vector that lies along, let's say, the x-axis.
Right.
SOH, CAHTOA tells us, remember,
Vaguely.
that the cosine of an angle is equal to the adjacent side divided by the hypotenuse.
Okay, I'm following so far. But how do those sides and hypotenuse, how do those actually relate to our vector and its components?
Okay, so picture this. The vector itself is like the hypotenuse of a right triangle.
Okay, I see that.
The component we're looking for, the one along the x-axis, that's our adjacent side. And the opposite side, well, that would be the component along the y-axis.
Ah, I get it. So to find the x component, we multiply the magnitude of our vector by the cosine of the angle.
Exactly. And to find the I component, we would use the sine of the angle because remember, SOH-CAH-TOA tells us sine equals opposite over hypotenuse.
Right. Okay, that's making more sense. But hold on, isn't decomposing a vector supposed to make things simpler? Now we're throwing trigonometry into the mix. How does that actually make things easier?
Okay, well, think back to our box pushing example.
Yeah, okay.
By decomposing that force, we've now separated out the part that's contributing to the box's forward motion, versus the part that's just pushing it down.
Right.
And this lets us actually apply Newton's laws of motion separately to each component, which makes the calculations a lot easier.
Okay. So instead of dealing with one sort of complicated force that's at an angle, we have these two simpler forces acting along our nice, neatly chosen axis.
Precisely. And this approach works in so many other scenarios, too. Like, for example, in projectile motion, we decompose that initial velocity into its horizontal and vertical components. And that lets us analyze how far the projectile travels horizontally, how long it stays in the air, all using those, equations of motion.
Oh, right.
You probably remember from physics class.
Wow. So like calculating the trajectory of a baseball after it's been hit, that uses this.
Yep. Or think about designing a bridge. Engineers, they have to decompose all the forces acting on the bridge to make sure that it can withstand the weight of traffic, the wind.
Wow.
By breaking those forces down into components, they can figure out how much stress each part of the bridge will actually experience.
It's crazy how something that seems so abstract, like breaking down a vector into these parts, is actually like the basis for so many real-world applications.
It really is. And honestly, we're just scratching the surface here. Once you really grasp those core concepts of vector decomposition, a whole world opens up.
I'm feeling a lot more confident about this now. We've talked about choosing our axes, using SOH, CAH-TOA to find the components, and even how this whole thing simplifies problem solving in the real world. Is there anything else we should cover before moving on?
Well, there is one common pitfall that people often stumble on. Remember, decomposing a vector doesn't change the vector itself. It's just a different way of representing the same information.
Okay.
It's like translating a book, into another language. The story's the same. It's just expressed in a different way.
Oh, so the original vector, it's still there, right?
Yeah.
It's still pointing off at that original angle. We've just kind of broken it down into these parts along our axes to make it easier to work with.
Exactly. The magnitude and direction of that original vector, they stay the same. We're just expressing them in terms of those components.
Okay.
Along the axis we've chosen.
That's a really important point.
Yeah.
So we've mastered the basics of decomposition. What's next? Where do we go from here?
Well, the simulation we've been using, and it actually has this really cool feature, we can rotate the axes.
Oh.
Which means we're not stuck with just horizontal and vertical anymore. We can choose any two perpendicular directions we want.
Wait, why would we want to rotate the axis? Wouldn't that just make things more complicated?
Not necessarily. Sometimes those standard horizontal and vertical axes, they're just not the most convenient or intuitive. Remember that ball rolling down the ramp?
Yeah.
Choosing axes that are actually aligned with the ramp makes analyzing the forces so much easier.
Oh, I see. It's like we're creating a custom coordinate system
Yeah.
that perfectly fits the problem we're trying to solve.
Exactly. And this kind of flexibility, it opens up a whole new level of problem solving. We can now deal with situations where the motion isn't just along, the straight lines anymore, like planets orbiting stars, cars going around curves, anything with those curved paths.
I'm starting to realize this is way more than just like a math trick. It's a whole new way of thinking about the world,
Right.
understanding how things move and interact.
You got it. That's what makes vector decomposition so powerful. It's not just about plugging numbers into equations. It's about understanding those underlying patterns,
Right.
the principles that govern the universe.
Okay, I'm sold.
Yeah.
Let's talk about some of those more complex scenarios where rotating the axis is like essential. I want to see how this all works in the real world.
Let's do it.
Yeah.
There are so many cool examples we can explore.
Okay, you've got me curious. Give me an example where this whole rotating axis thing really comes in handy. Like, what kind of problem would make me go, thank goodness I can choose my axis?
Okay, picture this. You're an engineer
Okay.
designing a roller coaster. Your job is to make sure it's both thrilling and safe, which means you got to understand all the forces that are acting on the cars as they go through the loops and the dips and the turns.
I'm already feeling a little queasy just thinking about those loops.
So now imagine trying to analyze all those forces. Using just our regular horizontal and vertical axes,
Yeah.
it would be a
I
nightmare.
can imagine, because at every point along the track, the direction of motion is changing, right? Gravity's always pulling down, but the normal force from the track, it's constantly shifting, pushing the cars inward as they go around those curves.
Yeah, so our standard up, down, left, right, that just wouldn't be very helpful here. It'd be like trying to fit square pegs into round holes.
Exactly.
Yeah.
And that's where the power of rotating the axis really shines. Instead of being stuck with that fixed coordinate system, we can actually align our axes with the direction of motion at any point along the track.
Okay.
So we might tilt our axes so that one point's along the track and the other point's perpendicular to it.
Oh, so we're basically creating a custom coordinate system. Yeah.
Like fits the curve of the track at that exact moment.
Precisely. And by doing that, we can break down those crazy forces into components that actually make sense. We can see how much force is pushing the car along the track, how much is pushing it inward, and make sure the track's actually designed to handle it all safely.
Wow, so something as simple as choosing the right axes can literally make or break the design of a roller coaster.
Absolutely. And this principle, it goes way beyond roller coasters. Think about airplanes banking as they turn, or, satellites orbiting the Earth. Anytime you have an object moving along a curved path, rotating the axis can be a total game changer for simplifying the analysis.
This deep dive has been amazing. We've gone from basic definitions of vectors to visualizing those components with the simulation, and now we're seeing how this all connects to these real-world applications. It's incredible.
Yeah. And remember, we're just scratching the surface here. Vector decomposition, it's this fundamental idea that underlies so much of how we understand the universe. As you keep learning, you'll find it popping up in all sorts of fields. Computer graphics, machine learning, who knows where else?
That's pretty cool. So to our listener, we encourage you to keep playing with that simulation. Test out different scenarios. See how choosing different axes changes the way you think about the problem.
Yeah, and don't be afraid to go beyond those textbook examples, Think about the forces acting on a skateboarder as they go up and down a ramp, or the motion of a pendulum swinging back and forth.
Right, there's a whole world of vectors out there.
Just waiting to be decomposed.
Awesome. Well, thanks for joining us for this deep dive. We hope you learned something new, and most importantly, that you're inspired to keep learning
Keep questioning.
and keep those vectors decomposed.